that you have a dismantled AC machine and dismantled DC machine on your laboratory table. You can feel it with your hand, with your eyes and brain. You can see it. You can take the measurements, and you prepare a report that how it looks like, or what are the parts of it, what the measurements, etc., etc. But here in this virtual class, there is no option for that. So I have gathered some pictures of AC and DC machine part-wise. That means, of course, the each picture represents different parts of every machine of AC and DC machine, and then we will see that, and we will go for the, and we will try to understand that what DC machine or AC machine how actually looks like, or how we can identify both of them. How we can distinguish between them, rather. Clear? Well. Okay. So here in the material I have from the laboratory, so here I can see the DC machine, whatever DC machine we have in our laboratory. The manufacturer is Siemens. Siemens is a company, you all know that it's a very renowned company, electrical and electronics company. So they manufactured that machine. Now, how you can find the manufacturer, that means details, or how you can find the basic details of the machine? That is from the nameplate. Nameplate is something which you can find over there. Just give me one moment. Just give me one moment, okay? Well, let me present you a screen. Well, can you see the screen? Can you see the picture of the machine?
Yes, sir.
Yes, sir.
Yes, sir.
So, yes, sir. In this machine, there is no nameplate is visible here, but actually the nameplate, if you look at the cursor, if you can see the cursor of the computer, you can see the nameplate will be something which is bolted, or which is on the frame. Okay. The nameplate is there, which is on the frame, which may be somewhere here. It is bolted on this frame. And in the nameplate, what are the informations that it contains? It contains the manufacturer's name. It contains the rated voltage of the machine. It contains the rated current of the machine, sometimes power of the machine, or it can contain the speed of the machine, well, number of poles, etc., etc. So these are the things. That means these are the data that nameplate actually contains. That means from a nameplate you can have an overview of a machine, that how this machine is, what the machine is. And there also the type of machine is also mentioned, that whether it is a DC machine or a AC machine or shunt machine, series machine, etc., etc. The type of the machine, that is also mentioned. So some basic characteristic informations are there in the nameplate. So nameplate contains that. Okay. Let me stop sharing the screen. Actually. Now. Well. Now what else? That is, then there is the rated output. The output is of the machine, what we have in our laboratory, that is has a 2 kilowatt. It is a 2 kilowatt machine, and that rated output is also given in the nameplate. Then the rated voltage, that is 110 volt. That means you cannot apply more than 110 volt to the machine, because if you apply that, apply more than 110 volt to the machine, the insulation was there that will be destroyed. Okay, so that means the rated voltage that depends on the design of the machine, and it is predetermined that I have that 110 volt machine, or I have the 220 volt machine, or I have the 415 volt machine. That means you cannot apply the voltage beyond that value. If you apply the voltage beyond that value, then the machine or the insulation of the machine will get destroyed, and the machine will be short circuited, and then it will burn, and it will be of no work. Fine. Then the rated current is also specified in the nameplate, and which is specified as 2 to 3.5 ampere. Actually, it should be a particular value, but here, whatever the manual I got from the lab, it is written that is 2 to 3.5 ampere. So it is, I think, that there should be a particular value. That means it may be either 2 ampere or it may be a 3.5 ampere. Well, if the rated current is not mentioned to you, if the rated output and the voltage is mentioned, then also you can calculate the rated current from these two values, because you know that for the DC machine, the voltage into current is equal to the rated output. There is no concept of power factor and all these things. Therefore, just simply if you divide the output voltage by output power by the voltage, you will get a current value, and that will be your rated current. Maybe something more than that, because the power losses are there, so maybe something more than that. Well, so let us consider that this is a 2 ampere machine. Okay, let us consider this is a 2 ampere machine. Well, the rated speed is 1500 RPM, that is specified. Oh, well, one more thing, that is rated current. What the rated current means? Rated current means if you apply the rated voltage to the machine, and if you are giving the machine under full load condition, running the machine under full load condition, that means you are utilizing the machine at its full capacity, then the current it will draw from the supply will be the rate, will be that much of current, that is the 2 ampere or 2 to 3.5 ampere, like that, whatever the rated current is that. So that is the rated current. Clear that whenever you are using the machine at its full capacity and you are giving the rated voltage, then the current it is drawing from the supply is basically the rated current. And the rated speed is, that is for our case, in our machine, whatever the machine we have in our laboratory is 1500 RPM. That means under rated load condition, that means under rated voltage applied, under rated load applied, the machine will run at the speed of 1500 RPM. Clear? So that is the rated speed. Then type of excitation, that is series, shunt, and compound, maybe whatever it is. So in our case, we have the compound machine. We have a series machine, we have a series winding, as well as we have a shunt winding also. And the temperature rise is 40 degrees above ambient. So temperature rise, sometimes it's mentioned, sometimes it's not. But in our case, the temperature rise is mentioned as 40 degrees above ambience. Well, now come to the armature. You can see the picture over here that I have presenting. So what is the armature? Armature is basically this one. This, if I don't know whether you can see the cursor or not. Let me. No, the pen is also not working, so you have to do it by your cursor. Okay. So if you can see the cursor, so you can see that this is the armature. Armature is a thing where we can extract the main power, or where we can provide or give the main power. In case of generator, we can extract the main power, or we extract the main power from the part of the machine that is called the armature. And in case of motor, where we give the power, main power, that is known as the armature. So in case of DC machine, the armature is basically the rotor. Clear? Armature is basically the rotor, because in DC machine, we normally extract the power from the armature, okay, and we give the power to the armature. And in the stator, there are the field windings. Clear? So in the stator, there are the field windings. So these are the field windings. You can see the marking over here that these are the field windings. These are the poles. These arc-like structures, these are the poles. Clear? And across the poles, there are the field windings. So when the current flows through the field winding, then it will produce a magnetic field which will pass through these poles, or through this metallic part, which is made of iron, and that acts as a pole. That means maybe north pole or south pole. If the fluxes are coming out of the pole or out of that metallic part, then it will be known as the north pole. And if the flux lines are going into the metallic part, then that metallic part will be known as the south pole. Now you can change the north pole and south pole in a machine by just changing the polarity of your supply, of your field supply. If you change the polarity of your field supply, your north pole will become the south pole, and the south pole will become the north pole. So in this way, you can change the polarity of the poles. Clear? Okay. Now this is the armature. Now what we have to do, you can see that in this armature, you have these brown parts over here, small brown parts, or here you have a brown part, you can see. So these brown parts are basically the conductors. Clear? These brown parts are basically the conductors, and where these brown parts or where these conductors are placed are known as the slots. Fine. And that metallic part which is there, if you can see the movement of the cursor, you can see that the metallic plate which is there in the armature, these are known as the teeth. Okay. So in between two teeth, there is one slot, and in between two slot, there is one teeth. So in this way, the the armature is constructed, and within the slot, the windings are placed. Clear? Now we know that if we give a field winding, or if we give the supply to the field winding, then there will be a magnetic field in the field winding. Magnetic field will be produced. Some north pole and south pole will be produced, and the magnetic field will be there. Now, if we inserted the rotor conductor or the rotor into the magnetic field, then what happens? That the conductor will be there inside the magnetic field. Clear? Now we know that if we make some arrangement where the current can flow through the conductor which are placed inside a magnetic field, then what will happen? Then according to Faraday's law, a force will be inserted on that current carrying conductor. Clear? If a simple conductor is inserted in a magnetic field, then nothing will happen. But if the conductor that means if somehow we can make the conductor current carrying, then on that current carrying conductor some force will be exerted, and the conductor tries to rotate or change its position or try to move. Clear? And similarly, on the other hand, if we insert some conductor in a magnetic field and we try to move it, or we try to give a movement to that conductor in some direction, then the current will start to flow, or the EMF will be induced due to the flux cut, and then the current starts to flow through that conductor. Clear? And that current, if we can extract that current, so we can extract the power from there. So that will be the generator. That will be the principle of generator. Now, the funny thing is that in case of a DC machine, a DC machine can be used like both as an generator or a motor. If you give supply to the armature, then it will act as a motor. Or if you give some movement to the armature, that means without any supply, if you give some movement to the armature by using a prime mover or something else, then it will act as a generator. That means it will generate the electricity, and you can extract the power from the armature. Okay, so these are the rotor. These are the conductor that I am saying, that the brown things are the conductors. Okay, now you can see that if you see the cursor, you can see that there are some brown parts, and there are some actually separated brown parts over here, isn't it? So these are known as the commutator. So every winding is connected to one commutator. Every winding is connected to one commutator. Clear? And in between two commutators, there is a insulation. That means there is a gap. They are not a solid thing. They are not connected to each other. They are separated with each other. Clear? And that commutator actually, that means extract the power from that winding and give it to the outer circuit through a brush. A brush will be placed over here. A brush will be placed over here and here. You can place a brush over here. So actually, the commutator slides over the brush. Brush is fixed. Commutator rotates because commutator is connected with the rotor, and it is connected with the rotor. So as the rotor rotates, the commutator also rotates because it is connected. But the brush, it is connected with the brush also. The commutator is connected with the brush, but they actually slide on the brushes. Brushes are fixed. Commutator is rotating, so they slide on each other. Fine. That means there is a continuous connection between the brushes and commutators. So therefore, whatever power, if you give some movement in out to the rotor inside the placed inside the magnetic field, if you give some movement to the rotor, then what will happen? Then according to Faraday's law, the EMF will be induced in the rotor conductor, and then the current will flow, and that current will come to this through this winding, flow through the winding, and that current will come to the commutator. Now where the current will go? Now from this commutator, that current will flow through the brushes. Will go to the brushes, which is placed over the commutators and which can slide over the commutators. Okay, and they are connected with each other. That means not solidly connected, but they can slide. So the current will come to the commutator, then it will go to the brushes. Brushes are made of carbon because of the self lubrication and the conducting property of carbon. So the carbon brushes, and then through the carbon brushes, we can extract that power, or we can extract that current to the external circuit, and we can light a bulb, or we can run any DC appliances. Clear? Okay. So that is the case. Well, now we have to take some measurement of this armature. Let me tell you one thing. Yeah. So if you see the armature separately, you can see the armature looks like this. That means whatever in the previous picture we have seen, we have seen the rotor was there, the stator was there. That means the armature and the field winding was there. So we have seen this togetherly. But if we see separately the armature looks like this. This is the armature or the rotor of a DC machine. Fine. Okay. These are the windings. These brown parts are the windings, and the slots. These are the teeths. And in between two teeth, there are the slot, and the windings are placed inside in the slot. And these are the insulations. See, here you can see some material is there which is not brown, not the metallic as well. So these are basically the insulation, and with that means the windings are separated from the teeth with that insulation. Clear? Okay. So now we have to take the measurement. That means we have to measure the diameter and length of the machine. So diameter will be you will have a caliper. That means we will have a caliper over there, and you can measure the diameter. So diameter is basically this is the thing. This is the diameter of the armature, and length of the armature is this. This is the length of the armature from this point to this point. This is the length of the armature. Fine. So the length, you have to measure the length and the diameter, but I can tell you the values. The diameter is the 15 centimeter and the length is 28 centimeters. Then you have to find out the number of slot. So you have to count the number of slot by your hand and how many slots are there. You have to find out, and that will be the 29 slots. In case of our machine, not all machines, because every machine has different number of slot, different diameter, different length, etc., etc. Okay, but in our machine, what the machine we have in the laboratory, so that have 29 number of slots. Now, what is slot pitch? Slot pitch is basically the distance between two slots. That means the distance between this and distance between this. These are the two consecutive slots. One is this one. This is one slot, and this is another slot. So you can, so this is the schematic diagram. Sorry, this is a schematic diagram. So these are the teeth. This is the teeth, and this is the slot. The groove is basically the slot. So the distance between two slot is known as the slot pitch. So how you can measure the distance between two slot? You can measure the periphery, that is pi into d, or 2 pi r, whatever it is. You have measured the diameter, so pi into d is enough. So pi into d divided by number of slot, that will give you the distance between two slot. Clear? Okay.
Yes, sir.
Now the number of ventilating ducts. What is ventilating duct? Ventilating ducts is, these are the ventilating ducts. That means some holes in the in the armature through which air or oil they can pass. Normally air can pass because for the oil cooling it will be a difficult construction. So you can say that the air the ventilating ducts are some holes inside the armature through which some fluid can pass, which actually the purpose of these holes or purpose of these ventilating ducts is basically to improve the ventilation so that the machine cannot get overheated. Clear? To reduce or to keep to keep the temperature of the machine within limit, we provide some ventilating ducts for the bigger machine, for the big machines. If you have the big machines, that means the big size machine, high power rating, etc., then we provide normally the ventilating ducts, because for that machine there is a very chance to get for the machine to get overheated. Clear? Therefore, for that type of machine, that means for the bigger machines, it is necessary to provide the ventilating ducts or this kind of holes in the armature. But for the small machine, the temperature rise will not be that much high. That means in that case, that means for the small machine, the ventilating duct may be there or may not be there. It is not necessary to provide the ventilating ducts for the small machines. In our case, we have no ventilating ducts. Okay. In our case, the armature looks like this, and there is no ventilating duct provided in the armature. Then we have is the armature laminated? This is the question is there, that is the armature laminated? If laminated, then why? Okay. So what is the lamination? First, we have to know that what are the laminations. If you look into this picture, this armature, very minutely, then you can see that this teeth part, they are not a solid part, isn't it? There are several very thin plates are there which are stacked together. You can see here this is one thin plate, then there is another thin plate, then there is another thin plate, and you can see that that means in between two thin plates there is a black line basically. So by that you can separate or you can distinguish that they are not a solid one. They are the combination or the stacking of a lot of thin plates. And these thin plates are known as the laminations. Clear? Well, now if you want to see the picture of one lamination, that looks like that looks like this, the cross section of one lamination. This is see, this is the slot, this is the teeth. This is the teeth means that that is visible to you. In the previous picture, whatever the metallic part visible to you is basically this one. This is the teeth, and the slot is not visible to you because inside the slot there are the windings. There were the windings in the previous case. So these are the slot. These are These are the teeth. So here teeth is marked. These are the cooling ducts, that the ventilating ducts over there. This lamination, if your machine is a bigger machine and if you want to provide some ventilating ducts, so you have to make that ventilating duct when you are making the laminations. Basically what we do not construct the whole core or the whole stator at a time. We actually construct the laminations, the thin metal plates with this kind of cutting. Clear? And we produce it several. That means maybe 100 or maybe more than that. Then we keep that 100 plates or 100 or 200 or 500 number of plates togetherly, one after one. We stack it one after one, and then its length become more and more. And then finally, when we bolt it with each other, then finally the core part of the machine has been prepared. And then in that, then there is a long groove, or the slot has been prepared, and within that slot we actually place the windings. Clear? Okay.
Yes, sir.
You can see a point over here, the slot for wedges. What is wedges? I'm coming to the later. but that means for the maximum machine you can find this, that is the slot for wedges. That means for the wedge is a part of a machine for which one groove is made, and through this groove the wedge is placed, and below or beneath the wedge we have the windings placed over here. We have the winding placed over here, and over the windings we place a wedge. Now what is wedge? I am coming to that. Okay, so before wedge, we have one more thing, that why the armature is laminated. So the answer is yes, the armature is laminated because we actually made the laminations first, and then we stacked the laminations, and then we made the that means the solid make the stator core or the rotor core or the armature core. What?
Current.
Huh?
The due to eddy current.
Yes, of course. And why the armatures are laminated? They are laminated to reduce the eddy current, because if you make it a solid one, see, if you make this thing a solid one, okay, then what will happen? That see the main thing, that is the main working principle, the main idea behind that machine is we are placing a conductor. These are the copper conductors. This brown things are the brown conductors are the copper conductors. So we are placing some copper conductor inside a field, which when carry the current, then there will be a force on them and they will move. Or if they move inside the magnetic field, then there will be an induced EMF and the current will flow through that. But the problem is that not only the copper is the conducting, but the iron is also a very good conductor of electricity. So therefore, when iron is placed on inside the magnetic field and we move that iron, or we move that iron, then the flux cut will happen to the iron also. And inside that iron part, there will be an induced EMF and there will be an induced current flowing through that iron part. So if a current flowing through the iron part, then what will happen? Then there will be a power loss inside the iron core or inside the iron part, and that power loss will be supplied by the supply. That means our supply. So therefore, our machine will not be very efficient because that power we are not using. We don't want to have any power loss in the iron. We want to have the power in the windings. Clear? So therefore, we have to minimize that power that is consumed by the iron part. That's why we are laminating all these things, because if we don't laminate, then the current will be very high. But as we make the thin plates and we stack one after another, we stack them one after another, then what will happen? Then the cross-sectional area of the current, that means the cross-sectional area of that laminations will be reduced. Okay, so we know that resistance R is equal to rho L by A. So if the cross-sectional area is reduced, then the resistance will be higher, and if the resistance is high, then the current will be low. The idea is basically that. So we have to make a resistor. We have to make make the resistance of that part very high, and for that reason, we actually laminate the armature. Armature is laminated. We actually make the armature by stacking some laminations to reduce the eddy current loss. Clear?
Yes, sir.
কে একটা জয়েন করতে চাইছে বাড়ি। Well, then what are the materials used for wedge and the armature? Well, now what is wedge? I'm coming to that. Okay. If you look at the picture very carefully, you can see that in between two slots, there are the windings. So we are fine. We can see the brown part over here. But in this slot, what is the slot gap is there? There, the brown part is not visible. Brown windings are not visible. But what is visible is basically a thing, the wooden thing, isn't it? It's like a wooden thing. From the color and the texture, you can see that, or you can tell that it's something which is made of wood or something like that.
Yes, sir. It looks like wood.
Yeah. So that is basically the wedge. What actually we do? So that means we place these wedges over here so that the armature windings so that the armature windings don't come out of the slot when they rotate. Because when a thing rotates, you have already learned in the physics in class 11 or 12 that whenever whenever any particle rotates, a centrifugal force is exerted on that, and that centrifugal force always try to move that particle away from the center, isn't it? So when the rotor rotates, the centrifugal force also applied on the conductors, and that centrifugal force try to move that conductors away from its center. That means it try to tear the windings. It will try to tear the windings. So therefore, the wedges are placed over here so that the windings don't come out from the slot. Okay, because if the windings come out from the slot, then there will be a short circuit. A dead short circuit will be there. They will connect to each other, and there will be a short circuit. So we have to place that windings inside the slot, and that's why we place a wedge over here, a wooden material which is a non-conducting. At the same time, it gives a good mechanical strength, and that is the thing. So this is the wedge. So wedge is made of the wood. And what is the armature armature is constructed? Armature means this lamination. These laminations are constructed from the silicon steel. Clear? And that is also true. And why the silicon steel is used? The laminations are used to reduce the eddy current loss. And the silicon steel, the material we have chosen to reduce the hysteresis loss. Because we know that in the iron there are two types of loss. One is hysteresis loss, another is the eddy current loss. Clear? Hysteresis loss is something that whenever you magnetize one iron body, then let us consider you have a magnetized one iron body. It is an electromagnet. You increase the field current and the magnetization. That means the intensity increased, and at some point there is a saturation. Now, if you try to demagnetize that, if you decrease the current, then you can see that whenever the current is zero, the magnetic property, that the magnetic field intensity is not zero. That means it retains some magnetic energy within that. So that is basically a loss, and that is the hysteresis loss. So to make the hysteresis loss smaller, we chose the material silicon steel to construct the armature. Clear? Well, the next question is the draw sketches of armature lamination. So you have to draw that. You can take the idea from this picture, or this picture like that. So you can take the idea from that. You can draw it by your own way, or you can take the help of internet and books. So it doesn't matter, but you have to draw it by yourself. Okay. Then we have to come to the field, because it is the field winding. Okay. Number of plane pole, number of interpole. Then we have to find out what is the pole, or we have to know what is pole and what are the interpoles. Okay. Let's go to the. Okay, see the wedges. The wedges looks like this. These are the wedges. Only simple wedges. So what you have to do? You have to place the conductor over here, and then in this slot, yeah. See here, the slot for wedges are there. So in this slot for wedges of this lamination, you have to place these materials. These are the wooden materials, and these are the wedges basically. Okay, so that will give you a mechanical strength so that the windings don't come out of the slot due to the centrifugal force when they rotate. So these are the wedges. Okay, now come to the poles. This is the poles. This is a stator winding. This is a stator of the of a DC machine, and you can see there are 4 number of poles up there. Clear? There are 4 poles. These are the field windings. The white part are the field windings. Now you can see that, sir, normally the windings are made of copper. So why they are white? Because copper is not white. Copper is brown. Of course, copper is brown, but there is a lamination is given over there. Okay, so every winding is laminated, and that's why the lamination is. I think they have used a paper lamination, so it is white. Clear? But the copper conductors are there inside the lamination, and that is brown. And in between two poles, two consecutive or big poles, that means this part, these white parts are basically their poles, main poles. Clear? And in between two main poles, you can see another thing which looks like a pole, because there is a metallic part over here, and then there is the windings over that metallic part. Here also in this 4th thing, you can see that. These are known as the interpoles. Clear? So these are the main poles. For these 4 are the main poles. The main poles look like this, and then there are the interpoles. There may be the interpoles. I cannot say that there are the interpoles. I must say that there may be the interpoles, because interpoles may be there or may not be there in a DC machine. Interpoles are optional. Interpoles actually, we provide the interpoles to reduce the armature reaction. Now, what is armature reaction? Armature reaction is something when the machine rotates, the flux actually gets distorted. So to make the flux steady and to prevent it from the distortion, we provide some extra pole, extra pole with the additive polarity, so that the flux do not get distorted or do not get distorted so much. Clear? Or to make the distortion or to reduce the distortion, we provide some additional poles. So these are known as the interpoles. Fine. So the interpoles may be present in a DC machine or may not be present in a DC machine, because if the construction is so that when the machine rotates, the flux do not get distorted so much, then we don't need to provide the interpole, because if you want to provide some interpole, it will add some cost. It will add some extra cost. So interpoles are provided only when it is absolutely necessary. Clear? So interpoles may be there or may not be there, but in our case now, whatever the machine we have in our laboratory, we have the interpoles. So the number of main poles will be 4 and number of interpole will be 4. Now pole arc and pole pitch. Now what is pole pitch? Pole pitch means the distance between two consecutive poles. Now two consecutive poles means either from the starting of this pole to the starting of other, that means the adjacent pole, or the end of this pole to the end of the adjacent pole, or from the middle of this pole to the middle of adjacent pole. So that will be the pole pitch. And pole pitch is find out the diameter, or you can measure the diameter. Actually, you can measure the diameter if you have a caliper. So you can measure the diameter over here, caliper and scale, of course. If you measure the diameter, then the pi d will be the periphery, and the pi d by 4. Here the number of pole, of course, is 4. So that's why by 4. If the number of pole will be 2, then it will be by 2. So the periphery divided by number of pole will give you the pole pitch. That means distance between two adjacent poles. And what is the pole arc? Pole arc is basically this. This is the pole arc. See, this is not a flat one, but this is the curvature is there. So this is the pole arc. Right? Okay. Now, if you can find the diameter, and if you can find the width of it by using a scale or the caliper, so you can find the arc from there. And the value of this pole arc is here, that is 9 centimeter, that is given in the manual. And the pole pitch is similarly pi d by number of poles, so that is 12.0951 centimeter. And the ratio of pole arc to pole pitch, that is 9 by 12.0951, that will be 0.7441. That is the ratio of pole arc to pole pitch. Now, the next question is, are the poles laminated? Yes, of course the poles are laminated. Of course the poles are laminated. Everything there that inside the machine is laminated except this core and the frame. So whatever winding is there, where the windings are placed, that may be the armature, that may be the field, they are laminated, because whenever the flux cut happens, that means the flux is flux is linked with some part of the machine, so that part should be laminated, because to reduce the eddy current loss. So similarly, so that's why the stator poles or the field system of a machine are also laminated. Okay. Now, is there any bevel on the pole shoe? Yes, there is a bevel on the pole shoe. Now, what is bevel? Bevel is, you can see that this the structure of the pole. I don't know whether I have a better picture or not. Yeah, this. If you see the schematic diagram, so this is the pole, the overall thing. This is the pole. This is the pole arc, because it's not a flat one. This is the bevel. This is the bevel, and this is the pole shoe. The total thing is known as the pole shoe. So there are the bevels. So this is the pole shoe. Bevel means, bevel is something which is prominent than others. It means whenever you use the Microsoft Word or Microsoft PowerPoint, you can modify, or you can design your writing, or you can design your picture or something in different way. So there you can find a option where there is a bevel. So bevel means basically you can see that there is inside the schematic diagram, whatever they're given in the Microsoft PowerPoint. So you can see that bevel is something what the inside there is a groove and the edges are carved, and they are actually something at a higher level than the base, like that. So the bevels are things that is more prominent than the others. So these are the bevels basically. So yes, the pole has the bevels, and this is known as the pole shoe. This part is known as the pole shoe, and pole shoe is always made which is higher in length than the main pole. This is the main pole. These are the field winding which is placed across the poles, and this is the pole shoe. Now, why the pole shoes are made like this and the arc-like structure? To this is done in this way to make the flux distributed evenly over the air gap. Clear? Because if you make it flat, then the armature, the rotor, whatever the rotor you have, rotor is of circular shape. It's a round shape, circular shape. Now, if you make it flat, then what will happen? Then at the tip, the air gap will be more, and at the middle, the air gap will be less. Fine. So that means air gap is more, means the reluctance will be more over here. The flux will not try to flow through that edges, and the flux will try to concentrate to the middle, like this. So the flux will be concentrated. It will not be distributed. So therefore, we have to make a structure like that in such a way so that the air gap become uniform, so that the field or the flux, the reluctance to the flux become uniform, and the flux flow uniformly through the air gap to the machine, and it do not get concentrated at a certain part. Okay, so that's why we made a structure like this, or we made the pole shoe, and the structure of the pole shoe is like that. The arc structure is given, and this is given to actually meet the requirement of the round shaped armature, because as it is rotating, so it has to be round shaped. The static thing is maybe any shape, but the round, whenever a thing is rotating, so that must be a round shaped thing. So to meet the demand of that round shaped armature, the pole arc or the pole shoes are made with like this structure, and the pole arc is given. Okay. Well, now the field coil. Does the machine have a shunt field coil? It is the first question. So in our case, yes, our machine has a shunt field coil, and our machine has a series field coil also. So it is a compound machine. So how you can see, or how you can identify a shunt field and a series field? You can see that in the field winding, that means here, in this picture, if you see, look at the main poles, and the main poles are, or the wide pole, that means if the field windings are open, that means if the machine is open and you can see the field winding, you can see the windings are there. But it may happen, or if it is a compound machine, you can see that there are two kind of wires, which is or by which the field winding is made of. There are two kind of wire. One is thin wire, which has a enormous number of turns. Okay, and you can see another you may see another type of winding where the conductor is thick. Conductor is not so thin. Conductor is thick, and a few number of turns, 2 or 3 number of turns, or 5 number of turns, or 10 number of turns are given there. You can measure. You can actually count the number of turns. So a thick winding with a lesser number of turns, and a very thin wire or thin winding with a huge number of turns. You can find two type of winding in a two type of winding in a field coil. Now, if you find that a field coil consists of only the thin wire and then with huge number of turns, then you can say that it is a shunt field machine. And if a machine consists of a field winding which have a thick wire, and it is consists of a few number of turns, then you can say that it is a series winding machine or series field machine. And if a machine have both what we have in our laboratory, that the machine has both kind of field winding, that is winding with which consists of a thin wire and huge number of turns, and another is consist of a thick wire and a small number of turns. So then you can say that it is a compound wound machine. That means that both the series field and the shunt field both are there. Now, why the series field is a series field winding is made of thin wire and huge number of turns? Because see, through the through the shunt field, if the field is placed at the shunt or the parallel to the armature in the shunt, then in that case the field current is very small. Clear? The field current should be very small because maximum current should be flow through the armature. The maximum current should flow through the armature. Maximum current, whatever it is drawing from the supply or it is giving to the supply, the maximum current should be there in the armature coil. Clear? And the shunt field should have a very small current. Now, as the shunt field has a very small current, then we have to make that current, that means that the resistance of that wire very high. So that's why if the resistance of that wire is very high, then it will draw the small current from the supply. If the voltage is same, because for the shunt machine, the voltage for the armature and voltage for the field both are same because they are placed in parallel. So the voltage are same. So if the resistance of the shunt coil is very high, then only the shunt current will be, or the field current will be very small. So to make the resistance very high, we have to make a very thin wire, because we know that R is equal to L by rho L by A. So if the A is small, then the resistance R will be high. So to make the resistance higher, we have to make a very small very thin wire. Now through that thin wire, when the small current is flowing, then how the required flux will be generated? How the required flux will be generated? Flux is generated from the ampere turns, that is the MMF, magnetomotive force. Simply, that means if you draw the analogy from the electrical circuit, you know that if there is a voltage, then there is the current. That means a current is flowing through a conductor. That means there must be some voltage across the conductor, and the voltage drives the current through the conductor. Similarly, the MMF is there. MMF is the magnetomotive force. Voltage is basically EMF, which is the electromotive force. That means which is a force which actually gives motions to the electrons, and it helps, or it makes the current flow. So magnetomotive force is some force which actually drives the flux, just like the EMF. Clear? So EMF drive the current and the MMF drive the flux. So the flux is there, that means some MMF will be there, and MMF means the ampere into turn. So here the current is very small through the shunt winding. So number of turn should be very high so that the MMF meet the requirement and the flux generated will be the required flux generated, that means which is required to make the machine run. Clear? So that's why that means using that very small current through the shunt winding, the shunt field, if we have to generate the required flux, we have to make the turns higher, because the MMF is basically ampere into turns. So if we have to keep, and that MMF drive the flux. So if we require if we have to produce the required amount of flux, then we have to have a required, that means the required amount of MMF. And that required amount of MMF, if the current is very high, then if we increase the turns, then the MMF will be same. Clear? So that's why through this small or the thin wire is made to make the current small, and the huge number of turns are there to make the MMF the reasonable one, so that the MMF is do not get very low or something. Okay, to get the required MMF, we have to make the turns number of turns very high. But in case of series field, the field winding is placed in series with the armature. That means whatever the armature current is there, that current flows through the field winding also. Clear? Whatever the armature current is there, that current is flowing through the field winding also. That means the current that I have previously told, that the maximum current, our main aim is to pass maximum current to the armature winding. So if the field coil is placed in the series with the armature winding, so we cannot restrict the current to the field winding. So whatever the current flowing through the armature winding, the current will be same through the field winding. That's why the field, that means in case of series field, the series machine, DC series machine, through the field winding, huge amount of current is flowing. So for that, if we want to have a required amount of flux, what we have to do? We have to make the MMF restricted. So we have to have a small number of turns because the current is very high, ampere is very high. So if we reduce the number of turns, then the MMF will be same. And in this way, we can get our required MMF and the flux for the machine. So that's why the series field is always have a thicker winding or thicker wire and small number of turns. And the shunt field always have a thin wire, a thin conductor, and a higher number of turns. Clear? So in this way, by just observing the field coils, you can distinguish that whether the machine is a series machine or a shunt machine or a compound machine. Clear? Okay. Then what we have? Okay, explain how we'll identify them, so that I have just told you. Then there is the yoke, material of yoke. What is yoke? Yoke is this one. Here in this picture. So this is the yoke, this outer part, the frame basically. The frame is the yoke, is there. This is not the yoke, this is the core. Okay, this is the pole, these are the interpole, this is the core, this part. But outside the core, what is there is known as the yoke. So if we have some other picture, then you can see it. Okay, this is, and also this is, huh?
The silvery part you are talking about?
Yeah, the outermost part, this one. Yeah, this part, the silvery part, exactly. This one. And with the part, the legs are connected. Legs of the machine, where that means through which the
outer frame of the total machine.
Yeah, exactly. The yoke is basically the outer frame of the outer part of the machine. Correct. Sorry. Outer part of the machine. And what is the material which is through which the yoke is made of? That is the cast iron. Yoke is made of the cast iron. Now, length and thickness of the yoke, length and thickness you have to measure through the calipers and scale. But whatever we have in our laboratory, that is the length is 31.8 centimeter and the thickness is 2.3 centimeter. Okay. Now the function of yoke. What the yoke actually do? Yoke actually supports the entire machine because it is the outermost part. So everything, whatever inside the machine, actually inside the yoke, placed inside the yoke. So it supports the entire machine, and at the same time, it provides a return path of the magnetic flux in the magnetic circuit. See, if you see the picture, let us consider that this is north pole, this is south pole, then this is north pole, this is south pole. Fine. So from this north pole, as this is the north pole, so from this north pole, the flux lines are coming out and going to the south pole. From this north pole, flux lines are coming out and going into the south pole. But this is not. But how this flux returns actually? So that flux returns through this yoke like this. So then this is coming out of north pole, going into the south pole, and then from the yoke it gets returned to this pole, and then it is again coming out from the north pole and it is going to the south pole. And similar thing happens over there also. Clear? So the yoke actually provides the support to the machine as well as the return path to the magnetic flux. Well, then the commutator. What is commutator? Commutator is this is the commutator. Actually, you can see the commutator over here. This is the commutator. In the armature, this is the commutator. Okay. If you zoom in, this is the commutator. Commutator are basically made of coppers, and they are connected. Each commutator is connected with a conductor, and the current actually whatever EMF is induced in the conductor, current flows to the conductors, and current comes to this commutator, and then from this commutator, the current goes to the brushes and then the outer circuit. So if you take a closer look to the commutator, it looks like this. This is the commutator. You can see each and every commutator is separated by mica lamination. Each and every commutator is separated by some lamination, which is the mica lamination. or the mica insulation, sorry. Each and every commutator is separated by mica insulation. No one is connected to each other. Clear? Because if they are connected to each other, then the positive and negative side of the DC machine will get shorted. So that's why, and the machine will burn. That's why the commutator, every commutator is or every single part is basically insulated, and there is the mica insulation in between two commutator segment. Now the diameter of the commutator, which is 10.5 centimeters, so you have to measure the diameter of the commutator, which will be this one, measure of the diameter. And the commutator diameter by armature diameter ratio you have to find out. So armature diameter you have find it out as 15 centimeter, and the commutator diameter is 10.5 centimeters, so it will be 0.7. Now number and width of commutator bar. Here you have to count the number of commutator bar. These are the commutator bar. You have to count the number. And you have to measure the width. Width means this, just this thickness. Okay, just this thickness. So the number of
actually we measured the following things. Means with which instrument do we measure the diameter of all these things?
Okay, the diameter it you can measure it with the calipers. The caliper is an instrument which we normally inside caliper and outside caliper are there. So inside calipers are used to measure the diameter or the length of this groove type element. Okay, this groove type element, that means inside inside part, and the outer caliper outer caliper is used to measure the outer diameter or outer length of some part of the machine, like that. Like if you want to have the outer diameter of this commutator ring, then you use the outside caliper. You place the outside caliper over there and you will get the diameter. But if you have to measure the inside diameter of this commutator ring, then you have to provide, if you have to take an inside caliper, you have to place that inside caliper into this hole, and you have to measure the diameter of this of this hole. Yeah.
Okay, sir.
So number and width of commutator bar. Number is 88, that is measured in our case, and the width is 0.4 centimeter. And the material of the commutator bar is basically hard drawn copper. Clear? It is hard drawn copper. The thickness of mica separation is 0.1 to 1 millimeter. Normally we give it as 0.1 millimeter. So 1 millimeter is not there. It is 0.1 millimeter actually. Okay. The 1 millimeter is wrongly written in the material I got. So it is 0.1 millimeter. Sorry, it is 0.1 centimeter or 1 millimeter. And the width of the commutator bar is 0.4 centimeter or it is 4 millimeter. Clear?
Sir, we will write only 0.1 centimeter.
0.1 centimeter, yeah. Mica separator, okay, 0.1 centimeter or 1 millimeter. Okay. Now, why the mica separator are used? Because it is an insulating agent. So every commutator should be insulated to each other, because otherwise the short circuit will happen. So that's why the mica separator are used basically. Well, is the mica separator undercut? No, it is not undercut. Undercut means if you place your hand, okay, if you place your hand over this commutator ring, you can find a very smooth structure, though the commutator, in between two commutator bar, there are the mica insulations. If that mica insulation is undercut, then you can find a groovy structure. If you slide your hand or if you move your hand on this commutator bar, so you will find a groovy structure. If the mica separator were undercut, because whenever there is the undercut, that means whenever there is the mica separator, if it was undercut, then it was beneath the level of the commutator bar. So your hand will feel a groove at that point. And whenever the commutator bar was there, your hand will feel a uprised thing. So you will feel a groovy structure over there. But it is not in the case for the DC machine, because in the DC machine, if we do a groovy structure like that, then our brush will get affected. So we have to make it very smooth. So therefore, there is no undercut. That means the height of this mica separator and the height of this commutator bar are the same. And if you place your hand, or if you move your hand through this commutator segment, or through the commutator ring, then you can find that this is a very smooth structure. You do not find any groove over there. So that means it is not undercut. Well, then the dimension of the riser. What is riser? Riser is this one. Yeah, this one. This is the riser. Okay, these are the risers. These are right. So dimension of the riser, you have to measure the dimension of the riser. The height is 12 centimeter, thickness is 1 centimeter, and width is 0.7 centimeter. So that is the measurement of the riser. And this part is known as the riser in the commutator segment. Well, then brush and brush holders. Brush and brush holder. Yeah, these are the brush holders. The brush holders looks like this. There is a spring attached with the holder, with every holder, and inside this holder the brush are placed. Brush are made of carbon, and brushes look like this. These are the brushes. Okay? So these brushes, these carbon brushes, are placed inside this brush holder, and they are they are attached to the commutator through this spring. The spring is there, so the spiral spring is there. So spiral spring actually insert a pressure on these brushes so that it is in contact with the commutator always. It always is in contact with the commutator. So that is achieved by these spiral springs. The spiral spring is always give a force on the brushes towards the commutator. So the brush holders looks like this, and the commutator and the brushes looks like this. And brushes are made of carbon. The number of brush arm over there in our machine, that is 4, and number of brushes per arm, that is 1. And the size of each brush holder, so axial length is 3.1 centimeter, and width is circumferential width is basically 2.8 centimeter. So that was the dimension of the brush holder. Okay. These are the brushes and brush holder. Now end frame. So this is the end frame. Clear? This is the end frame. It looks like this. ধরো end frame এখানে একটু দেখে নি আছে কিনা, এখানে কি দেখানো আছে? এখানে সেরকম ভাবে দেখানো নেই। আচ্ছা, এখন কোটা জয়েন করছে 1 মিনিট।
স্যার আগের ফিগারটা মনে ছিল।
হ্যাঁ দাঁড়াও দেখছি। এইটাতে তো দেখিনি, একবার একটুখানি দেখে নি জাস্ট ছবিগুলো কোনটাতে আছে। না এই দিকটাতে নেই, ঠিক আছে। এইটা থেকেই দেখে নিতে হবে, অসুবিধা কিছু নেই। দিস ইজ দ্য এন্ড ফ্রেম বেসিক্যালি। এন্ড ফ্রেম মানে হচ্ছে যে at the end, that means at the end means this part, মানে এটা হচ্ছে মেশিনের ধরো ফ্রেম, this is the shaft, these are the stator winding, this is the rotor winding. So at the end, whatever is there, whatever frame part is there, that is the end frame. Because we know that the machines are either semi-enclosed or closed. So this is a semi-enclosed machine. In a semi-enclosed machine, the end frame is not a closed one. But in a closed machine, the end frame is a closed thing. Like এখানে না end frame টা তোমাদেরকে ক্লোজ এটা দেখানো হয়নি, না এখানে নেই, কিছু করার নেই। যাই হোক, মানে যেমন ধরো see like this is the closed machine, this is a closed DC machine. So here there you have the magnet, and this is the yoke, okay, the core or yoke is there. Then you have the rotor winding over there. So if you put these parts together, so it will be a compact machine, and you cannot see anything outside the machine, from outside the machine. Okay, so that is a compact machine, that is a closed machine. So in that case, the end plate, so like this one, this is the end plate. So end plate is a closed plate. So you cannot see anything inside that means from the outside. You can see a whole machine, a compact machine over there. But here in this case, the end frame is not a closed frame. It is a semi-closed frame. That means it consists of only the bearings and the 4 arms. The arms are connected with the yoke or the body of the machine, and the bearing are there, which is there actually to hold the rotor, or to rotate the rotor. So this is a semi-enclosed type. Semi-enclosed type DC machine or semi-enclosed type end ring is there. And in our case, the type of the end frame is also the semi-enclosed. Now, do they support bearing or not? Yes, they do, of course, because semi-enclosed, because the function of the end ring is to hold the bearings actually, and the bearings are made of the cast steel. Okay, the bearings are made of cast steel. The type of bearing we used is basically the ball bearing. We know the ball bearing because ball bearing are normally everywhere in the cycle, in the motorcycle, in every household thing where the rotating part is there. So ball bearing is there. Ball bearing actually supports the rotor. It consists of two parts, actually three parts. Yeah, see. These are the bearing. It consists of three parts. One is the outer part, okay. One is the inner part, and inside this outer and inner, or in between this outer and inner part, there are the balls. Therefore, if you fix the outer part, the inner part can rotate very smoothly with the help of the rotation of these balls. So whenever the inner part rotates, the balls rotates itself, and actually that's why the inner part rotates. So actually the friction becomes very less in case of ball bearing. And that's the work. That's the actually the idea of the bearing. That means there will be a static part and there will be a rotating part, and the static part and rotating part will rotate over the static part, and the friction will be very small, because if the friction will be high, then there will be a corrosion over there. So the friction should be very small, and that is achieved by the ball bearing. So the shaft of the machine is fixed with the inside or the inner part of the bearing. The shaft is fixed, and the end frame is fixed with the outer part of the bearing. So now the end frame can hold the shaft or the total armature or the overall armature with the help of the bearing, and armature can also rotate inside the stator part. Clear? So that is the bearing actually. Bearing consists of three parts. One is outer, another outer ring, inner ring, and the balls. And this is placed somewhere over here and here. And in the both sides the bearings are placed, because otherwise there will be of no use. At both sides you have to place the bearings. So these are the ball bearing. And type of lubrication, we normally use grease for the bearing. You can see if you go to any cycle repair shop, you can see that the ball bearings that is mounted inside the axle. There is the wheel axle. There is there in the wheel axle. So that's why the wheel can move. And sometime if you take your cycle to the repairing shop, then they will dismantle the cycle. They will take out the bearings and they will grease that. They'll clear it and then grease it in or put some new grease over there. So grease is basically for the lubrication. And here also, in case of ball bearing, we use the grease lubrication. And the shaft diameter is 3 centimeters. Shaft diameter means this one. This is the shaft diameter. Okay. So shaft diameter is 3 centimeters basically. So these are the commutator part. This is the shaft, and all these things are there. Clear? Okay. So this is the construction of DC machine. And now we have to come to the construction of AC machine. AC machine looks like this. This is a 3-phase induction motor. This is the rotor part, and this is the stator part. It also has a nameplate. It also has a nameplate. And whatever induction motor we have in our laboratory, the manufacturer name is the Bhowmik Engineers, which is a company of Calcutta. The rated output is 2.2 kilowatt or 3 HP, and the rated voltage is 415 volt. Current output is 5.2 ampere. Speed is 1410 RPM. The number of pole is 4. So all these things are mentioned in the nameplate. Okay. Well, now number of pole is 4, that is given. Even if the number of pole is not given to you, then you can find the number of poles, because we know that formula, that is for the induction machine, the synchronous speed That means the speed at which the rotating magnetic field rotates, that is the synchronous speed, is basically given by the formula, that is 120 F by P. Clear? So if the number of F is constant, F is constant, F is the supply frequency. Supply frequency is 50 hertz, which is a constant in India, which is 60 hertz in America, like that. So for every country, the supply frequency is constant. it is fixed one. So the F is fixed. For India, it is 50 hertz. So 120 F by P. Now, if you have a number of pole is equal to 2, then you will get the synchronous speed is equal to 3000 rpm. If you have a number of pole is equal to 4, then you will get the synchronous speed as the 1500 rpm, like that. So if you see that the rated speed is mentioned like something 1410 rpm, then it is obvious that the synchronous speed will be 1500 rpm and the number of pole will be 4. If the rated speed is given something 2890 or 2940, like that, then it is obvious that the synchronous speed is 3000 rpm, and that means the number of poles is equal to 2. Now, number of pole cannot be less than 2. So the speed of an induction motor is maximum, that is 3000 rpm. That is the synchronous speed, and the rated speed will be maximum maybe 29. That means 2940, 2950, like that, or yeah, that is the maximum rated speed. Well, the temperature rise, it is also above the 40 degree centigrade above the temperature. Above the ambience. The frequency is 50 hertz. Insulation is E-type insulation, and duty cycle is 1, like that. Okay. Now come to the stator part. So these are the nameplate data. Whatever we have written over here, that means whatever we have told till now are the nameplate data for the squirrel cage induction motor. So all these things are normally specified in the nameplate, but something maybe not specified in the nameplate, like number of pole, or the temperature rise, or maybe the duty cycle. It may be specified in the nameplate or may not be. But what the maker's name, the rated output, rated voltage, speed, etc. These are the basic 4 things that should be mentioned in the nameplate. Now come to the stator winding. So this is the stator, basically rotor. Now you have to take the diameter of the stator. Diameter of the stator is basically this one. This is the diameter from this point to this point. Okay, so this is the diameter of the stator. The diameter of the rotor will be from this point to this point. This will be the diameter of the rotor. Okay. Now number of slot. Okay, the diameter of the stator is 14.3 centimeter, and number of slot is, you have to count the number of slots. Like 1, 2, 3, 4, like that. So when you have a physical machine in your hand, you can count it. And in our machine, it is the number of slot is 36. Now angular slot pitch. Angular slot pitch is basically the total overall angle. So these are the slots. These are the slots, and these slots are distributed over an angle of 2 pi radian, isn't it? Because from this point, if you go in an angular way, so it will, if you come to this point again, so you will cover 360 degree. That means 2 pi radian. So the angular displacement or angular that means the angular travel is basically the 2 pi for the whole stator part. So that means the angular slot pitch is basically 2 pi by number of slot, that is 36. So 2 pi by 36, that means 1.1745 radians. Clear? That is the angular slot pitch. Mind it, that is not the linear slot pitch. That is the angular slot pitch. So angular slot, if it is the linear slot pitch, then you have to go with the 2 pi, pi d by s. That means the number of slot, pi d by number of slot. That will be the linear slot pitch, and the angular slot pitch is 2 pi by number of slot. Clear? Now material is used for core, that is the silicon steel. Silicon steel, again silicon steel, because to reduce the hysteresis loss, and that is laminated also, just like the DC machine, that is laminated also, and lamination is given there to reduce the eddy current loss. So lamination, we normally, to reduce the eddy current loss, we give the lamination, and to reduce the hysteresis loss, we use the material silicon steel. Clear? Okay. And wedge is also there for, and that is made of wood, so wedge is there. which is made of wood, and just like the previous case. Okay, is the stator laminated? Yes, of course the stator is laminated. And why? It's the same thing to reduce the eddy current loss. The next question is draw the sketch of the stator. So you have to draw the sketch of the stator. You can take an idea from here, this picture, or you can take an idea from this picture like that. Okay. Well, one thing is that is if you can see the picture, you can see that there is this picture gives you an idea of rotating magnetic field. The rotating magnetic field means these are the windings. This is one winding, this is one winding. So there are the windings over there in the stator, which is fluorescent blue colored. Okay, so when the windings are excited with the supply, then the magnetic field is produced inside the machine. We all know that. In the case of DC machine, the same thing happens. But here, the thing is that we are actually giving a three-phase supply. Okay, we are giving a three-phase supply. Three-phase supply means balanced three-phase supply. That is the magnitude of the current. The magnitude of the voltage or the current of the supply magnitude are the same in the three phases, and they are separated from each other, or they are displaced from each other by an angle of 120 degree. Clear? So and why 120 degree? Because there are three phases, and if you distribute these three phases in a circular manner, in a circular manner and in a symmetry, then you will find that every phase will have a displacement of 120 degree from each other, because 3 into 120 equal to 360 basically. So that is the concept. So you have 120 degree displaced windings placed over here. That means in the slot 120 degree displaced winding. So one winding is there, another winding will be here, and another winding will be here. Okay. So these are the 120 degree displaced winding, and in this 120 degree displaced winding, we are giving a three-phase balance supply. Three-phase balance supply means where the voltage and current magnitude are same in three phases, but that three phases are 120 degrees separated from each other in time domain. That means at one instant, if you take a look at the three phases, then you can find that three phases are 120 degrees separated in the time domain basically. So the time domain separation is there 120 degree, and the spatial separation, that means in space domain the windings are separated at 120 degree also. So that's why this displacement or this separation of in time and space domain actually create a magnetic field which rotates. Clear? Which rotates, which is not a static one, which rotates, and that is the rotating magnetic field. And that's the beauty of induction motor, that induction motor is self-starting and all these things comes to later on. So the rotating magnetic field is produced inside the induction machine. But in case of DC machine, the rotating magnetic field is not produced. The magnetic field is static. If you give a supply to the armature, then the force will be created, and then the machine will rotate as a motor. Or if you rotate the motor, or if you rotate the armature or rotate the machine, then the EMF will be induced in the armature winding, and then you can get the power. Clear? That means you have to give a field supply and an armature supply separately for the DC machine. But for the AC, for the induction machine, you don't have to give two separate supply or separate supply to the two kind of windings. You have two windings over here. One is stator winding, one is rotor winding, of course. But if you give the three-phase supply in the stator winding, the rotating magnetic field will be created, and that rotating magnetic field will make the rotor rotate in its own direction. That means in which direction the rotating magnetic field is rotating, the rotor will rotate in the same direction. And that works on the principle of transformer, because whenever there is a rotating magnetic field is there, and the rotor is placed inside that rotating magnetic field, then of course the flux cut was there, because the field is rotating. So the flux cut is obviously will be there. So as the flux cut will be there, then the EMF will be induced in the rotor, and the current will flow through the rotor windings. The rotor will produce its own magnetic field, and these two rotating magnetic field will collide. That means will contradict, or will not contradict, but these two will act upon each other, and they will produce a torque, and that torque will make the rotor rotate. So that is the basic idea behind the induction motor, working principle of induction motor. Okay. So you have to make a diagram of stator winding from this. You can take the idea from here or this picture or anything from internet like that. Detailed view of stator. Mhm. Okay, let me take you through this. See, in this picture, you can see that these are the stator windings are placed over there. In this picture, also you can see that these are the stator. This is the stator. These are the slots. Okay, this is the teeth. Windings are placed inside the slots like that. But these are also laminated, and the laminations looks like this. These are the lamination. The thin plates are the lamination. They are stacked together, and then the stator core actually formed. This is the core. This part is the core. This white part. Sorry, white part is the core. These groove are the slot. These are the teeth. And when this overall thing is the lamination, and when this a number of laminations are stacked together, then the stator is formed without winding, of course, because you have to place the windings over here. Yeah, see, like this. This is the stator slot. This is an actual machine. A man is placing the winding inside the slot. So these are the slots. See that in every slot there are the papered insulation. Okay, so that the slot and the winding do not get shorted with each other. So they are the paper insulation, and this man is placing the winding inside the slot. So these are the slot. This is the placed. These windings are already placed in the slot, but these slots are still vacant, and he will place some the machine. The windings over there. So these are basically the slot, and this is the teeth. This is the slot. The groove is the slot, and this is the teeth. Clear? So this is not a schematic. This is the actual picture. This is picture. This is a figure. It looks like this. These are laminations. Well, this is the rotor. The rotor is basically of two types. One is squirrel cage rotor, which looks like this, and another is the slip ring rotor, which looks like this. The slip ring rotor means slip ring rotor has three rings on the shaft. And it has three brushes which can slide over the rings, just like the DC machine commutator. What happens that the windings are coming out of the slot. Windings are placed inside the slot actually. Then they are coming out, and then each phase, the windings coming out from each phase. We have three phases. So windings coming out from each phase is connected to one slip ring. So from A phase or from R phase, there is one slip ring. From windings from Y phase, that is coming to this slip ring, and windings from B phase, that is coming to this slip ring, the third slip ring. Okay. And now the three brushes are there. So brushes are static, and this whole part is rotating. This rotor and slip rings all are rotating. So similarly, like the DC machine, the currents from R phase, Y phase, and B phase come to these slip rings, and then it goes to the brushes, and through the brushes, they goes to the outer circuit, like that. Okay. These three slip rings actually made shorted by some external resistance, and in this way, the current flow through this through the slip ring induction motor. You can say it at wound rotor also. We all sometimes we say wound rotor, because in the rotor the windings are wound. That's why they are wound rotor. And another type of rotor is the squirrel cage rotor. Squirrel cage rotor is this one. See, this is the squirrel cage rotor. So you can see that in the squirrel cage there is no slip ring, there is no winding, nothing is there. What they have are basically the rotor bars. Squirrel cage rotor do not have any windings. Squirrel cage rotor have rotor bars. Now you can say that in the previous case, the EMF is induced in the rotor winding, the current flows through the rotor, the current in each phase, current from R phase coming to the one slip ring, current from B phase coming to one slip ring, and current from C phase coming to another slip ring, and that slip rings are connected with the brushes, or they are actually connected, but they are not permanently connected. They can slide over the brushes. So brushes, and through that brushes, the current goes to the outer circuit. Okay. But how this In this way, how the current flows. Actually, here when this rotor or this squirrel cage rotor rotates inside a magnetic field or inside a rotating magnetic field, so the EMF also induced in the rotor bars. Here no winding is there. Here the bars are there. These are the bars. These are the bars. These small lines. These are the bars. Okay. So the bars are there. So EMF is induced in the rotor bars, and the current flows to the rotor bars. But how the current flows to the rotor bar? Because if the circuit is not closed, then the current cannot flow. Of course, the circuit is closed, and that circuit is closed by this part. This is known as the end ring. Okay, this is known as the end ring. Every rotor bar, is connected to this end ring, and this end ring is there at the both side of the rotor. So the every rotor bar are connected to each other. You can see a picture where, yeah, this. See, these are the rotor bars. Okay, these are the rotor bars, and this is the end ring. So every rotor bar is connected to each other with the end ring. So that means when the EMF is induced in this bar, the current will flow through this bar and it will come to this way. So these way all are shorted. So, and it is a three-phase, it is an AC alternating magnetic field. So when the EMF is positive over here, so that means positive means, let us consider that the direction of current is from left to from right to left. This is the positive. So when the direction of current is from right to left in this bar, then at the dead opposite in this bar, the direction of current is from left to right, because this is AC. Okay, so in this way, in some bar the current is going to from left to right, and then it is coming to the end ring, and some other bar it is going from left to, from some bar it is coming from right to left, and then it is going to the end ring, and then it is coming back to some other bar and it is flowing from left to right, and then it is going through that end ring also, and then it is coming like that. This is the cycle. This is the closed circuit. Clear? And these are the rotor laminations. Here the plate disc-like structures. These are the rotor lamination, and that disc-like structure has a groove. These are the slots, and the bars are placed inside the slots, and and in between two grooves or in between two slots there is the teeth. Clear? And physically the machine or the armature, or the rotor winding, squirrel cage rotor looks like this. So these are the bars. They are shorted with the end ring. These are the ventilating ducts. It is necessary for the higher range, higher rating machine or the bigger machine, and not necessary for the smaller machine. So that I have already told in case of DC machine. But this is the thing. This is the structure. This is a squirrel cage rotor. Okay. Well, so the rotor diameter is 9.1 centimeter. Number of slot, you have to count the number of slot. How you can count it? You can simply, we have a squirrel cage, of course. In our laboratory, we have a squirrel cage machine. So your rotor will look like this. So you have to count these lines, and you have to find the number of rotor slot. Now the slot pitch is similarly pi d by number of slot. Whether the rotor slots are parallel to the axis, this is one question, whether the rotor slots are parallel to the axis. Of course they're parallel to the axis, but they are not again parallel to the axis because they're skewed. You can see that if they are completely parallel to the axis, then what will happen? Then if one starts from here, that means if one bar starts from here, then it should go just in parallel with the shaft, and it will come to this point. It should come to this point, isn't it? It should come to this point, but it is not coming to this point. Like DC machine, see, in DC machine, what we have, these are the windings for the DC machine. See, the slots are just parallel to the axis, just parallel, dead parallel to the axis there. But in case of AC machine or in case of three-phase induction motor, see, the windings or the bars are not parallel to each other. Not exactly parallel to the axis, but they're skewed. Clear? So they are skewed. If they're parallel, then it will be like this. It should be like this. just parallel to the axis. But it is not like that. It is something skewed. So that is written over here. Now, whether there are any conductor, there is any conductor. There are conductors, but they are bars in form of bars. In case of squirrel cage machine, they are bars. But in case of wound rotor, there are the wires, simple like conductors like that. But of course, the conductors are there. But in case of squirrel cage, they are in form of bar, or rotor bar. The material for conductor, that is the aluminium or copper. Ventilating duct, no. Width of duct, so if the ventilating duct is not there, so width of duct is not there. Is the rotor laminated? Yes, of course the rotor is laminated, because you can see in these pictures. See here, if you take a close look, you can see that these are the plates, very thin plates, just like the DC machine. They're very thin plates stacked with each other. Clear? That is for the wound rotor, that means for the slip ring machine. And in case of and in case of squirrel cage machine also, you can see that there are also this is laminated, because these are thin plates of lamination, thin laminations are there. See here, if you take a very close look, you can see there the thin laminations, that is laminated. And the rotor is also laminated to this for the same reason, to reduce the eddy current losses. So that means the squirrel cage and the slip ring, both rotors are laminated, are made laminated, and that is to reduce the eddy current loss. Now, what are the materials used for? That is the materials used, that is core. For core, it is silicon steel to reduce the hysteresis loss, and the wedge, it is wood. Why the rotor is called squirrel cage? Squirrel cage because you can see in this picture that it gives you a cage-like structure, isn't it? It looks like a cage. That's why it is known as a squirrel cage. Then draw the sketch of the rotor. You have to draw it. I have nothing to do. The stator housing. Stator housing is basically nothing but the yoke or the frame. So material of the frame is the cast iron, and the frame is basically this. This is the frame of a three-phase induction motor. This is a frame. This is made of a cast iron, and it is actually molded. That means it is not connected. It is not like that some parts are there and they are welded to each other. It is complete one part, a single piece. Okay. So the iron, the melted iron is actually poured inside a mold, and the thing is made as one piece. Yeah. So the frame is this one, and the material is cast iron. So length and thickness of the stator housing. The length you have to measure. So this is the length, this is the length, and this is the thickness. Clear? Length is 21.5 centimeter and thickness is 1.75 centimeter. Function of stator housing is same, to support the poles and to increase the internal stability, and to provide a return path to the flux. That is the purpose of the stator housing or the frame. Okay. Now fan type of cooling. Type of cooling is a fan cooling. Why fan cooling? Because that means this. Normally our machine looks like this. So you can see that normally almost all the machines have a fan mounted on the shaft over here. So this fan is actually there for the cooling purpose, and fan has a cover. You can see this is the fan cover. Okay, this black part is basically the fan cover, and inside that fan cover the fan is there. This is the nameplate. This is the terminal box. This is the terminal box. You can see here there are the 6 terminals are there. What is the 6 terminal? 2 terminal for R phase, 2 terminal for Y phase, and 2 terminals for B phase. Now if you connect the one R phase, Y phase, and B phase together and give supply to another terminal of R phase, Y phase, and B phase, then it will be a star connected. And if you connect the one, if you give the supply to the 3 phases, that means 3 terminal of RY and B, and keep the other terminal of the RY and B like a delta, then it will be a delta connected winding. So you have a provision to make the winding as per your convenience. Maybe you can make the delta winding, you can make the star winding. In case of this motor, where the 6 terminals are available to you. But if the 6 terminals are not available to you, if you have 4 terminal available or 3 terminal available, that means the connection, that is either the machine works as star or delta, that is connected inside, you cannot access it. Whether the machine is connected in star, then you have to start the machine as a, or you have to run the machine as a star connected machine. Or if the machine internally connected as a delta, then you have to run the machine as a delta connected machine. You cannot change the connection because they are internally connected. But if you have the access of all these 6 terminals, then you can change the connection as per your convenience. So that is the facility of accessing these 6 terminals. Clear? Well, we are talking about the fan. So this is the fan, and it looks like this. You can see that normal fan, whatever fan we have or we have seen, the table fan, the ceiling fan, or whatever fan we have seen till now, the fan blades are not parallel like this. That is not the straight. Fan blades are normally some tilted, isn't it? Why the fan blades are tilted? Fan blades are tilted at one side to give the wind a particular direction, isn't it? See, our ceiling fan has a tilting at a particular angle or at a particular direction. Our ceiling fan blades has a particular tilting. Why it is tilted? Because to force the wind downwards direction, force the wind towards the downward direction. Clear? The table fan has also a tilting over there, so that when the table fan rotates, the wind flows in a particular direction. But you can see that in this case, the fan blades are just parallel to each other. They are not tilted. Why? That means here our intention is not to provide the air to a particular direction. Now, why we are not intended to provide the air in a particular direction, or to provide the air in a particular direction? Because if you because the induction motor or any motor can move in both directions. Clear? Any motor can move in both directions. It can move clockwise or it can move anti-clockwise. In case of 3-phase induction motor, if you give R, Y, and B connection like this, that here it is R, here it is Y, and here it is B. So let us consider the motor rotates in the clockwise direction. But if you change the phase sequence, then RBY, if you make it RBY instead of RYB, then the motor will rotate in the counterclockwise direction. Now, if we tilt the blades in a particular direction to give the wind a particular direction, then what will happen? Then let us consider that when the machine rotates in the clockwise direction, then the wind flow towards the inside the machine, and it cools the machine. Okay. But when we change the phase sequence, then what will happen? Then the wind come out from the machine, and the machine will not be the cool. That means it cannot cool the machine. Okay, so the ventilation will not be proper, and the ventilation will be inferior when the motor rotates at the counterclockwise direction, and the ventilation will be superior when the motor rotates at the clockwise direction. So to eliminate that problem, we actually don't tilt the fan blades of any machine. We normally keep the fan blades straight, so that whether it rotates at a counterclockwise or the clockwise direction or any direction it rotates, the ventilation will not get affected. That means every direction of rotation will get the same ventilation. Clear? That's why the fan blades are parallel to each other and they are not tilted. They're flat plates. Okay. Then shaft and bearing. Of course, the shaft has a driving and non-driving end, and in both driving and non-driving end, we have the bearing, and we use the ball bearing. The lubrication is grease. The shaft diameter, outside diameter is 3.34 centimeter, and length is 14.5 centimeter. Well, shaft key is there. So if you see the shaft, okay. Let's take a closer look at this. This is the rotor. This is the bearing. The ball bearing is used over here. So this is the shaft, and this is the shaft key. Okay. Why the shaft key is given? Shaft key is given because if you want to couple two or more machines with each other, okay, if you want to couple two or more machines with each other, then the shaft key plays the key role, because you can lock the two shaft of the machine with the help of this key. If you place one another bar to or another another bar, the iron bar over there in this groove, and that bar will connect the another shaft groove of another machine, then that two machine will be connected. So when you want to couple two machines, then the shaft key comes into the play. So this is known as the shaft key. Okay, and this is the shaft. And what is the driving and non-driving end? Driving end means where you have the shaft extension. So shaft extension is basically the driving end. That means from that end of the shaft you can extract the mechanical power. With that end of the shaft you can connect some things, as that means some other machines or some other load, so you can connect that. And the non-driving end, normally we have the fan. See this is the driving end of the shaft. Here the key is there, key groove is there, keyhole, shaft key is there. Okay, so this is the driving end, and the non-driving end is normally not accessible. Non-driving end has the fan. Clear? Okay.
Yes, sir.
So I think this is all. Okay, shaft key dimension is also required, because the key wire dimension, that is length is 6 centimeter, width is 0.8, and depth is 0.4 centimeter. Okay, so that's all for today. This is in this way we can study the AC and DC machines. And thanks to Swapnil to provide the materials and help me out there. I can do one thing. I can share the photos whatever I have shown to you today, if it is required to you, if it is required, so I can share it with you.
Sir, share it actually. And sir, what is the date of submission of the file?
Date of submission take 1 week from today.
Okay, sir. Okay, sir. Sir, I will try to collect it by next week Monday, 12, and I will submit it today. Next week Tuesday.
Okay, fine. Next Monday.
And one thing, that is, what will be the date of experiment? Today's date, right?
No, date of experiment. Don't make it today. Okay. So make it today. Give the date as today, because I will talk to SR sir, and I will say that I have to reschedule the thing. So I took the class on that way. So give the date at today.
Okay, sir.
Sir, and you said to take the rated current for DC machines as 2 ampere.
Rated current. The rated current, actually the Swapnil sent me the material, and there let me check. The rated current was given
2 to 3.5 ampere.
2 to 3.5. So okay, fine, you can write it, but I think it should be the 2 ampere, because 2 ampere into 102 volt. So that means 2 kilowatt 2 ampere. One second. 2 kilowatt is 2000 watts divided by 110 volt. It's 18 point something দেখাচ্ছে, 18 ampere দেখাচ্ছে। কি ছিল রেটেড কারেন্ট? আমি রেটেড কারেন্ট অ্যাকচুয়ালি ভুলে গেছি কত ছিল ওখানে।
স্যার মানে ওটাতে কি 2 অ্যাম্পিয়ারই লিখবো, কনসিডার করব, নাকি 2 to 3?
দেখো একটা জিনিস সেটা খেয়াল করো, সেটা হচ্ছে রেটেড আউটপুট বলছে 2 কিলোওয়াট।
2 কিলোওয়াট
মানে 2000 ওয়াট।
হ্যাঁ,
আর রেটেড ভোল্টেজ হচ্ছে 110 ভোল্ট। এখন ডিসি মেশিনের ক্ষেত্রে আমি যদি আউটপুটকে ভোল্টেজ দিয়ে ডিভাইড করি, তাহলে আমার কারেন্ট পাওয়া উচিত, কারণ হচ্ছে V * I = পাওয়ার।
হ্যাঁ,
এখন তাহলে যদি আমি 2000 কে 110 দিয়ে ভাগ করি, তাহলে মোটামুটি আমার আসে হচ্ছে 18 অ্যাম্পিয়ারের মতন। অথচ এখানে তাহলে রেটেড কারেন্ট হচ্ছে 18, কিন্তু এখানে দিয়েছে রেটেড কারেন্ট = 2 to 3.5। আমার 18 নয়, অ্যাটলিস্ট 15 হওয়া উচিত আমার রেটেড কারেন্ট।
হ্যাঁ,
এই আশপাশে থাকা উচিত, কিন্তু এখানে দেওয়া আছে 2 থেকে 3.5 অ্যাম্পিয়ার। এইটা আমার একটু ঝোলাচ্ছে, মানে একটু খটকা লাগছে এটা, যে কেন এটা এরকম হয়েছে।
স্যার ওটা আই থিঙ্ক কোনো হিউম্যান এররের জন্য হয়েছে বেসিক্যালি। এবার
হতে পারে ওটা কোনো একটা কারণে হতে পারে, ওইটা তোমরা একটুখানি দেখে নিও। যদি আর কোনো ইয়ে থাকে, মানে অন্য কোনো যদি হচ্ছে তোমাদের কাছে মেটেরিয়ালস কিছু থেকে থাকে, তাহলে সেটা একটু দেখো। যদি একই থাকে তাহলে বুঝবে যে ঠিক আছে, ওটা কিছুটা মানে গন্ডগোল হয়েছে, ওটা আমাকে দেখতে হবে গিয়ে। আর যদি দেখো যে না ওটা আলাদা আছে, তাহলে এরকম যদি ভ্যালু থাকে তাহলে সেটা লিখে দিও।
অ্যাকচুয়ালি স্যার যেটা হয়েছে আর কি স্যার, মানে আগের ইয়ারে সবাই মানে সিনিয়ররা বললো যে ওরা মানে প্র্যাকটিক্যাল ল্যাবই করেছিল।
হুম হুম
এবারে আমি যা মানে যেই সিনিয়রের কাছ থেকে এটা পাই, উনি কিন্তু জাস্ট মানে ল্যাবটার আই থিঙ্ক পিডিএফটা বানিয়ে রেখে দিয়েছিল আর কি, তাই আর কি ওনার কাছে আছে। তো মানে
আচ্ছা,
সবার কাছে পাবো কিনা সেটা আমি ঠিক
তাহলে
শিওর না,
কিনা
তাও
সেটা একটা ব্যাপার, এক্স্যাক্টলি।
আমি জিজ্ঞেস করে নিচ্ছি অন্যদেরকে, যদি কারো কাছে থাকে তাহলে একবার মিলিয়ে নেবো। আর
হ্যাঁ,
নাহলে কি স্যার ওই রেটিংটাই
নইলে এটাই
লিখবো?
লিখে দেবে, নইলে লিখে দেবে, এটাই কিচ্ছু অসুবিধা নেই।
ওকে স্যার, ঠিক আছে।
যদি যদি পাও তো ভালো, নইলে পরে লিখে দেবে। একবার একটু দেখো খুঁজে, এই আর কি।
হ্যাঁ স্যার, ঠিক আছে।
অত চাপ নেওয়ার কোনো কারণ নেই।
ওকে স্যার।
ঠিক আছে, ওকে, থ্যাংক ইউ। তাহলে আজকের ক্লাস তো এখানেই শেষ হলো। আচ্ছা, অ্যাটেন্ডেন্স কি স্বপ্নিল নিয়ে নিয়েছো, নিয়ে নেবে?
হ্যাঁ স্যার, আমি নিয়ে নিয়েছি।
তুমি নিয়ে নিয়েছো? আচ্ছা ঠিক আছে, তাহলে আমি আর অ্যাটেন্ডেন্স নিচ্ছি না।
স্যার আমি আপনাকে এই রাত্রির মধ্যে পাঠাচ্ছি আর কি, মানে
হ্যাঁ হ্যাঁ,
ওটা
তুমি করে পাঠাও, অত তাড়াহুড়ো কিছু নেই, তুমি করে পাঠাও না, অসুবিধা নেই।
হ্যাঁ স্যার, ঠিক আছে।
ঠিক ঠিক আছে, থ্যাংক ইউ এভরিবডি।
থ্যাংক ইউ স্যার।
থ্যাংক ইউ স্যার।
আচ্ছা আচ্ছা, কারো কোনো প্রশ্ন নেই তো, কোনো এনি
না
কোশ্চেন?
স্যার, সবাই মনে হয় নেক্সট ক্লাসের জন্য এবার আস্তে আস্তে লিভ করে গেছে আর কি।
আচ্ছা ঠিক আছে, ঠিক আছে, চলো
ওকে স্যার, থ্যাংক ইউ।
আমিও লিভ করে গেলাম তাহলে। হ্যাঁ, থ্যাংক ইউ ভেরি মাচ।